100% renewable energy supply, or still an energy supply dominated by fossil fuel in 50 years? Just like our energy demand, it is impossible to precisely predict our future energy supply. We only have expectations and wishes on the energy sources and technology we will utilize and how large the capacity should be. However, it does help us to prepare for the future by envisioning different scenarios of how our energy supply may look like. In the previous lecture, we worked with two demand scenarios. On the one hand, you had the business as usual scenario, where Delft does not implement any policy changes. And on the other hand, there was the new wind scenario. In the new wind scenario, the government focuses on efficiency measures and implementation of renewables in power generation and transport. If we now take a look at the conversion sector of the 2015 energy balance, we see that apart from the 5 petajoule of hydro energy, Delft's power is predominantly generated through the combustion of coal and gas. See the shares and efficiencies here. In the business as usual scenario, we assume that the share of power generation with coal and natural gas does not change. In the meantime, their efficiency improves at 1% per year. In terms of renewables, only the generation volume of hydropower increases at an annual rate of 3%. In 2030, Delft's energy balance looks as follows for the business as usual scenario. In the conversion sector, differences with 2015 are present in the increased amount of renewable energy, while the coal and natural gas input decreased due to the improved efficiency. In the total primary energy supply, there is a decrease from 2013 petajoule to 201 petajoule in 2030. But even more interesting is to explore how Delft will cope with the new wind scenario in its energy supply. As part of the new wind strategy, the government will also implement measures on the supply side. First of all, in 2030, 30% of the total electricity use should be originating from renewable sources. To reach this goal, the government will support projects in the field of wind, solar and bioenergy by means of feed-in tariffs. We expect that most of the growth will come from wind and solar. But also bioenergy will take a small share in electricity production. So how will these policy changes impact the energy supply into Delft? How will the energy balance look like for this scenario in 2030? Let's answer these questions. Here you see the 2030 energy balance in which only the energy use part, the lower section, is filled in. This information comes from the previous lecture on energy demand. We will now fill in the conversion sectors step by step. We can start by filling in the net flow of energy from the refineries. For an oil refinery, the input is oil, while the output are oil products, which places both input and output in one cell as a net flow. Here we see that the net flow is negative, which makes sense as refineries have an efficiency lower than 100%. This means that the energy input is higher than the energy output, hence, when we subtract the input from the output, we get a negative value. Do you remember that the new wind strategy also included a biofuel blending policy? The 7 petajoule of biofuel consumption by transport in 2030 is produced locally in biofuel plants with an efficiency of 85%. To produce the 7 petajoule of biofuel, 8 petajoule of biomass is required. Knowing this, we can fill in the cell for the biofuel refineries. Here the output 7 petajoule minus the input 8 petajoule equals a net flow of -1 petajoule. After completing the refineries row, we shall now look at the power plants. In 2030, 37 petajoule of power will have to be generated, as a TFC of electricity equals 36 petajoule, and the refineries require 1 petajoule of electricity. From this 37 petajoule, 30%, equal to 11 petajoule, has to originate from renewable sources in 2030. With the proposed incentives for wind, solar and hydropower, it is expected that 9 petajoule will originate from these sources. This means that 2 petajoule should be generated in biomass power plants in order to fill the gap in 2030. The 2 petajoule is generated in biomass power plants with an efficiency of 35%. This means that an input of 6 petajoule is required in terms of biomass. When we do the math, we see that a significant share of 26 petajoule will still have to be generated with fossil fuels in 2030. First of all, natural gas will play a significant role. However, the government did include measures to curtail the growth of natural gas use. Long-term contracts between the government and energy companies shall keep the power generation from natural gas constant at a 2015 value of 16 petajoule. To generate 16 petajoule of power with natural gas at an efficiency of 52%, 31 petajoule of natural gas input is required. For the power generation, in the new wind strategy, coal has the lowest preference among the energy carriers. Coal is used to fill the gap between the electricity use and the current renewable and natural gas-based generation. To generate the remaining 10 petajoule of power with coal at an efficiency of 41% in 2030, 24 petajoule of coal input is required. Furthermore, in the power generation section, no oil is used. We can now complete the energy balance by filling in the TPS row and the total column. We determine the TPS values by taking the TFC values and subsequently subtract the conversion values. The total column is filled in by just summing up the values in the rows. This is now how the energy balance can look like for Delft in 2030 as a consequence of the new wind policies. Note that we left out the energy winning section in this example as it would get too comprehensive. One thing to be aware of: 1 petajoule of electricity production from wind or solar counts for just 1 petajoule of primary energy, whereas 1 petajoule of electricity from other sources counts for 2 to 3 petajoule primary energy. So the actual contribution from renewables is more important than you can tell from the energy balance. With the new wind blowing into Delft, this is how the total primary energy supply may develop in the period from 2015 to 2030. In line with the decrease in the TFC, which we observed in the previous lecture, we see that TPS is also decreasing. The introduction of bioenergy into Delft can also be observed in this graph, while the other renewable sources are steadily growing. In 2030, Delft is not quite there yet, as fossil fuels still dominate the scene. However, it is nice to see that the amount of coal and oil in the primary energy supply is significantly decreasing towards 2030, while natural gas decrease is less strong. Remember that the policies included measures to make coal less attractive for power generation compared to renewables and to a lesser extent natural gas. In this lecture, you have been run through a possible scenario for the energy supply in a country. We looked at aspects like the introduction of renewables, efficiency improvement, and policies which are discouraging the use of fossil fuels. It was a very simple example, but it provides you with some insights on the approach you can take in constructing future scenarios. In reality, energy scenarios are way more comprehensive and complex. I invite you to think about plausible scenarios for your country and post your ideas in the discussion forum after this lecture. Thank you.